Hello viewers, welcome back to part 2 of our lecture on variational formulation in finite element methods. Now in part 2 we will dive into energy methods and see a complete mathematical derivation using practical example. Principle of minimum total potential energy. Now we come to know one of the elegant principles in mechanics, the principle minimum total potential energy. This principle is beautiful both mathematically and philosophically. Let me explain what it says. The fundamental statement. Among all possible displacement fields that satisfy the essential boundary conditions, we call these kinematically admissible displacement fields. Nature always selects the configuration that minimizes the total potential energy. Think about this for a moment. It always chooses the path of least energy. A ball rolls a ball rolls down the hill to the lowest point. A soap bubble forms a sphere to minimize surface energy. Similarly, a loaded structure deforms to minimize its potential energy. This is a profound variational principle that governs all of mechanics. The energy functional. We express total potential energy using a mathematical function called energy functional. That is, pi is equal to integral of u into dv minus integral of b into u into dv minus integral of t into u into ds. So the first integral form, let me explain one by one. Integral of u into dv. The integral of u into dv is nothing but it is called the internal of strain energy density over the volume. U represents the strain energy density stored in material when it deforms. The second term is integral of B into U into dV. Here B represents the body force. This entire term, that is integral of B into U dV, is called work done by body forces. The term B and U is the dot product, that is force time displacement in the direction of force. The negative sign is important because when external forces do work, they reduce potential energy of the system. Just like when you lower a weight, its potential energy decreases. And the third term, that is T into U ds, it is nothing but the negative work done of surface traction. T represents surface traction, that is force per unit area applied on the surface of the body. ds means integrating over the surface area. Therefore, total potential energy, putting it together, potential energy pi is equal to internal energy minus external work done. The minimization statement. The minimization statement, now comes the principle. The actual solution, the displacement field that actually occurs in nature, let's call it as u of x, that satisfies the condition dou pi equal to 0. What does that mean? It means any infinite variation in displacement will increase the total potential energy. The system is stationary point, specifically a minimum. Imagine a ball in a valley. If you move it slightly in any direction, it goes uphill. Energy increases. That's exactly what dou pi equal to 0. The equivalence of the equilibrium. This stationary condition, dou pi equal to 0, is mathematically equivalent to the equilibrium equations. Finding the displacement that minimizes energy is the same as solving the equilibrium equations. This gives an alternative route to solve mechanics problems. This energy approach is far more powerful in developing computational methods like finite element method. So let us see an example. You can see the example in the slide, that is the one-dimensional element. It is an axially loaded bar. So here if you see the problem, first consider the bar of length L, right? The cross section area is A, assumed to be a constant, and its Young's modulus is denoted by capital E, that is the material property. So the loading conditions, you can see there are two kinds of loading conditions. One is the axially loaded and one is the concentrated loaded, right? So if you use the axially loading condition, that is F, along the length of the element, that is force per unit length. And if you see the concentrated load P, that is applied load, that is at the right end, if you see X equal to L. And the support conditions, there are different support conditions. According to this example, you can see the fixed end at the left end is x equal to 0 and free at the x equal to length, which means initially the length of the element at one point is 0 and another point it is L. So let us see how the problem is solved by step by step. So you can see on the slide, the first step is by multiplying the test function, right? And the second step we have to integrate over the domain, and step number 3 is integrating each part, and finally you have to apply the boundary condition. So this is what the important step, because if you apply boundary condition, then only you can get the appropriate results. So let us see, meet in the another part. Thank you.